Evening, everybody. It is 5 o'clock on Tuesday, and we got some calculus to do. So just a couple of things to mention real quick before we get going into 12.3. Number one, you've gotten through the first quiz, so now if you haven't taken a quiz in one of these courses before, you have an idea of what that looks like. Just a reminder, there's a review for the quiz, so you can practice those, and a topics list for every quiz. We'll actually be finishing up module 2, which is over chapter 12 today. So the next quiz will be coming up fairly soon. So make sure you keep an eye out for that on the calendar. The other reminder is take-home problems. Remember, they're not due until the midterm, but if you want to turn them in early, you certainly can. Our next take-home problem for module 2 will, oh, thanks, Robbie. It's, okay, next quiz is this Saturday. Perfect. Thanks for sharing it. Take-home problem number 2 is going to be available after class tonight because it's going to be over module 2, which we are finishing today. All right. Again, the take-home problems aren't due until the midterm, which is sometime in mid-March. Dates on the calendar, but you can turn those in early if you like. All right, let's get into this. So you guys went through the video lessons, so this will be a little bit of a recap. I want to point a couple things out, especially in 12.3 and a few things in 12.4. But then I'm gonna try and have some good time for group work to let you work on the worksheets. So 12.3 is about arc length and curvature. The arc length concept is actually the same concept as what we did in Calculus 2 when we used a definite integral to find the length of a curve. And if you did the length of a curve given parametrically, it's actually the exact same, except now we're doing it in 3D instead of just 2D. So this is just what we talked about the last couple classes. We started talking about a vector valued function given by r of t. And basically, this is just a way of organizing parametric equations of our space curve. All right. And then the velocity vector is the derivative of the position vector. We also talked about the instantaneous speed, which is the magnitude of the velocity vector. Now, back in Calc 2, the same idea held. Basically, we take the definite integral of the speed to get the total distance traveled along a curve, or the length of a curve. It's the same idea here. So since we know the speed, and now remember, v is basically the derivative of our position vector. So just just as kind of a reminder, r prime of t is v of t. So a lot of times we're going to be starting with r of t and then working from there. But once we have the speed, which is basically the magnitude of the velocity vector, then to find the distance traveled along a curve or the length of a curve, hence arc length, all we do is we take the integral from a to b of the magnitude of our velocity vector, or basically our speed. A and b would be given in a problem, so we'd be looking from one point to another point. And those, it's important also to point out now, notice our integral is in terms of t. A and b would be t values. So for instance, when we were looking at those curves of like the helix, that look kind of like a slinky. And if we wanted to find the total length, well, this would be our starting t value. So that would be where t equals a. And this would be our ending value where t equals b. Okay. So that's arc length. There's nothing tricky going on with arc length. It's as straightforward as it seems. We'll get a chance to practice one here in a little bit on the worksheet. As I've told you before, don't worry about memorizing formulas because you're going to have the note card for those. So all we care about is how do we use these formulas, when do we use them, why do we use them. So this is our arc length. Let's, I think you can find an arc length pretty straightforward. So next thing we want to talk about is curvature. The curvature measures how quickly or sharply a curve bends. All right. And you can think real quickly why we might care about this, right? Think about a racetrack. You know, if we have a shallow curve versus a steep curve, well, here we'd have a small curvature. Here we'd have a large curvature because we have more bend in our curve. The curvature of a straight line is 0. So it makes sense, right? There's no curvature. And here's something that's interesting that I wanted to make sure we touch on. The curvature of a circle is k, which is 1 over the radius. Now, this actually always holds. So the curvature, which we're calling k, is always 1 over the radius, even on one of these curves. Because the way this works, the way the reason that as curvature gets bigger, radius gets smaller, you know, if I put in a circle here, let's make that as circular as possible, to fill in that spot, there we go. The radius would be the radius of the circle that would fit on that curve. Well, contrast that with putting a circle on this curve, right? We can see that the circle would be much larger and have a much larger radius. So that's why we have that reciprocal relationship between curvature and the radius. The radius is referring to a circle that, if drawn along the curvature, what its radius would be. And so a question could ask you for either. It could ask you for the curvature at a point, or it could ask you for the radius at a point, which is just 1 over the curvature. All right. I want to make sure we made that distinction in here. More often than not, we'll just find the curvature because once we have one, we have the other. But I think it's interesting to think about the relationship and why these things have a radius when they're not actually a circle. So now let's talk about curvature in terms of tangent vectors, because this is where the formula comes from. So the sharper the turn, the more the tangent vectors must change in the direction we're going. So we've got this more shallow turn. If we think of a tangent line moving across that, it doesn't have to change very quickly. Is everybody having issues with my voice cutting out? Or are you guys able to hear me okay?
Yeah, it's choppy a bit.
Okay. Has it been happening the whole time?
Yeah.
Any better now? Okay. Let me see if I can find a microphone. Give me just a second. Is it better now, or is it still staticky?
It's better now.
Okay. Let me know if it starts cutting out, guys. I can switch to a different microphone if it's a microphone issue, for sure. So just let me know. But if it's sounding more like normal, okay, better. Okay. All right, so let me recap what I was talking about with curvature, and then we'll move on from there. So so curvature again is basically how sharp we have on a turn. The sharper the turn, the higher the curvature. Now there's also a radius, which is the reciprocal of the curvature, because if we were to put a circle along that curvature, the radius would be the radius of that circle. So that's why the higher the curvature, the smaller the radius, and vice versa. The smaller the curvature, the larger the radius. So what we had started talking about before, when the mic was cut, when you guys let me know the mic was cutting out, is let's think about going along one of these curves as a changing tangent line. So a tangent line has to change a little slower along this curve, this larger curve or more shallow curve, than it does along this steeper curve. So now the tangent lines are changing direction more quickly, all right? That's going to feed into to the formula you guys saw from the video lesson for curvature. So I'm just going to talk a little bit about the formula. You're going to get a chance to try it here when we work on the worksheet in a little bit. Well, technically, the curvature can be thought of as a rate of change because what the curvature is a change in the tangent line with respect to a change in the arc length. So it really actually is a rate of change. It's kind of cool. So this is right on right on cue, Cooper. The magnitude of the rate of change of the direction of the unit vector with respect to arc length. So basically, if t is our tangent vector, and guys, this is the same tangent vector from last time. That's the derivative of your position vector divided by the magnitude because it's a unit tangent vector. So just again, as just a little reminder, oops, wrong tool, that t of t is r of t over the magnitude of r prime of t. And we found a tangent vector last time. Got the hats on these guys since they're vectors. All right, so that's essentially what the curvature is. It is the change in tangent line with respect to a change in arc length. Now it's an instantaneous change, so it's happening at an instant. So if we were to use this formula, the tangent vector must be defined in terms of arc length. That's what S is representing. A lot of times we use the letter S for arc length. What we're going to do is take that and modify it into a form that's more usable for us. So we're going to apply the chain rule. So we use the chain rule here to rewrite this. And dt is the derivative of the tangent vector, the unit tangent vector with respect to time, which would be the second derivative of the position vector divided by the magnitude of the first derivative of the position vector. And don't worry about that. I'm just trying to I want to make all the connections. That's not the most important part. Divided by the change in arc length with respect to time. So we're now putting all this together. We can rewrite it as t prime of t, the magnitude of t prime of t divided by the magnitude of r prime of t. Now, why can we do that? Well, S is our arc length, and it's the integral from a to b of r prime of t. So taking the derivative of both sides with respect to t means that we would basically, if you can remember from our fundamental theorem, that means ds dt is equal to the magnitude of v of t. Oops. Well, the magnitude of v of t, that's the magnitude of r prime of t. So the reason I'm going through this, guys, you got the formulas in the video lesson. I just want to make the connections for you because I want you to get at least a sense of where some of these formulas are coming from. So that takes care of where this part came from. That's why we can say, oh, the magnitude of ds via chain rule is the magnitude of ds dt, and we can calculate it here. This
Can you
guy
explain
is
how the
just,
chain rule works there?
oh, say that again, sorry, Cooper.
Can you explain how the chain rule works in the middle?
Right here.
Mm-hmm.
So we're kind of doing the reverse of the chain rule because, you know, the way that this would work, how do I want to put this? Basically what's happening, you know, if we're doing dt dt divided by ds dt, well, when we divide by a fraction, we flip and multiply. Oops, dt over ds. Those would cancel, and there's our dt dt.
Got it.
So that's kind of an informal proof of why these two things are equal, but it's the chain rule that allows us to do that. All right. So all this stuff is kind of building from what we did last time. So right here, this is what we'll call formula number one, because we're going to have, as you saw it in the videos, but there's going to be two formulas for arc length. This is number one. And if r prime of t comes out to be a constant, this one, the magnitude, this is a good one to use. It's very straightforward. We have another formula that you saw in the videos that looks like this. I'm not going to go through how you get from one to the other because the proof does take a little while. But if you want to see why these two forms are equal, if you go to 12.3 in the textbook, in the appendix, it shows the equivalence. It's hard to see intuitively why one is equal to the other, but I can tell you because you're doing a lot of unit vectors on the top, that's why you keep getting this larger power of the magnitude of r prime. So we have both formulas, and we're going to use both formulas. But again, the first one is this first one, which I think I said, I kind of call that number one. That one's great if that comes out to be constant. In other words, when you take the derivative of r, if you take the derivative of your position vector and then take its magnitude, if that comes out to be a constant, by all means, use this one. If that doesn't happen, this one is actually the better one to use, number two here. The downside of number two is because you're doing a cross product, you're doing a derivative here, a second derivative here, there's more opportunities to make a little math mistake, right? As we saw in the cross product, it's real easy to get signs conflated. But this is the more general form that will always work regardless of if r prime of t, its magnitude, comes out to be a constant or not. Okay? So we're going to have both formulas in our toolkit, and in the one I'm going to have you do in the worksheet, you're actually going to use both formulas to verify they come out to be the same thing. Okay? And that's our little rundown of arc length and curvature. What they are, you know, conceptually, I think that they're pretty intuitive. You guys have seen arc length before. Curvature, we've all driven around a curve, and the tighter the curve, the more we feel that force and the more we feel that rate pulling us to the side. So it's now just a matter of being able to calculate them. Questions at this point? All right, then here's what I want to do. Actually, that didn't take too much time, which is kind of nice. I put this in chat already, but I'll put it in here again. Let's do, since we just did the formulas, let's do the 12.3 worksheet. All groups are going to do the same problems, just number 1 and 2. Don't worry about 3. It's a longer problem. We won't have time to get to that one in here. And what we'll do is we'll take, probably the next 40 minutes if we need it to work on this worksheet, problems 1 and 2. And then around between 6 and 6:10, we'll come back together and we'll talk about 12.4. If you guys get finished sooner than that, that's great. But I want you to try 1 and 2 since we just got done talking about it. All right. All right. Any questions before we break into groups? All right, let's do this. Okay. So the question that came up was, doesn't magnitude always come out to be a constant? It does not, because it depends on what R is, right? So if we have, I'm kind of making one up off the top of my head, so bear with me here.
Or we can't see.
Is it not shared? Oh,
it says you started screen sharing, but it's black. There you go. That's good. Yeah.
Let's just say we have, and now when I do when we go to find the magnitude of R prime, we would have 3t squared negative sine t 0. And then when we do the magnitude of, R prime of t, we would have the square root of 9t to the 4th plus sine squared t, and then plus 0 squared. So I'm just going to, we'll write that on there. This is going to be something that is going to be in terms of t, so it's not a constant. A good example of, actually, the one you guys are going to do on the worksheet is a good example of one where it does come out to be a constant, because you're going to be able to use a Pythagorean identity when you calculate the magnitude. So we're not guaranteed it comes out to be a constant. And thanks for keeping me updated on the screen share, guys. Other questions? Okay. All right, let's do this. So you got the worksheet. Let's see, we got 13. So, all right. Should have an invitation, and you guys got the link to the worksheet. And don't forget, the answer key is on the second page. So let's see how this goes. Just number 1 and number 2. Don't worry about 3. All right, guys, welcome back. Good work. Make sure you get your solutions to 1 and 2 posted sometime before Thursday afternoon. You guys have been doing an excellent job of that, by the way, so keep it up. I wanted to mention one thing that we didn't talk about before I broke into groups that may or may not have come up in your groups before we move on to the next section, which we're just going to talk about a little bit. One of the things when you're doing curvature, if we bring over the worksheet, one of the things you get asked, right, is to calculate the curvature at a specific value. Now for 2, the curvature comes out to be the same whether you plug in 0, pi over 4, or pi over 2, because everything worked out to be constant. For problems like number 3, that's not the case. And so what I wanted to mention is when you should plug the t values in that case, all right? Because this is important. You should always do your derivatives first before you plug in any t value. So if you're starting with a position vector like this, you should find your r prime of t, your r double prime of t, your unit tangent vector and the derivative of your unit tangent vector. You're going to want those before you plug in these t values, okay? Now, that said, once you have those, then you can plug in the t values. So for instance, if we're using this formula here, so for number 3, you would want to use the alternative formula. You're not going to want to use this one. It gets to be a mess. But when we're using this formula, before you take the cross product, but after you've taken the derivatives, so after you found r prime and r double prime, then you'll plug in, let's say we're doing the first one here, then you'll plug in 0.2 for t, and you'll get vectors that are all constants. Then you'll take the cross product, okay? So I just want to talk a little bit about the order because it didn't really matter in number 2, but in number 3, now you can take the cross product, then plug the t value in, but as you can imagine, that cross product can get to be a mess, especially if you're doing it by hand. So my recommendation is to plug the t value in before taking the cross product. But always take your derivatives first, because think about it, and this is going all the way back to Calc 1, the function evaluated at 0 is not necessarily equal to the derivative evaluated at 0, is not necessarily equal to the second derivative evaluated at 0. Same thing goes with r prime, and r double prime. So you do your derivatives first, then after that, before you do the cross product, is when you can go ahead and plug your t value in, okay? So just want to make that clarification. All right, we got a little bit of time left. I just want to talk a little bit about the next section, 12.4. We don't need to spend a lot of time on this. It's not a big section for us right now. But you saw this about cylindrical and spherical coordinates. This is going to become a bigger topic actually after spring break when we start looking at some what are called iterated integrals. Don't worry about that term right now. We'll get to that in about a month and a half. But I do want to talk about the coordinate systems, and I want to mention a couple of things. All right. So we've been using rectangular coordinates. Why do we call it rectangular? Well, because as we saw in 3D, any point looks like a corner of a rectangle because it's made up of linear, horizontal, and vertical distances from the origin. Now in 2D, we had polar. So you guys should have seen polar either in trig or pre-calc, and hopefully again, at least a little bit in Calc 2. So polar actually only involves the distance from the origin and the angle with respect to the positive x-axis, okay? So here would be a point in polar. It's the distance from the origin and then the angle made with the positive x-axis. So some xy point in rectangular could be given as some r comma theta point in polar. And our conversions all come from right angle trig. So I'm going to go through this a little quicker, guys. I put the link to the PowerPoint both in chat and it's available in more. So if you want to get any of these conversions, you can just download the PowerPoint. But this is all straight out of right angle trig, because if I drop a vertical down here, I've got a right triangle, and that's where all these come from. So we're not going to worry about changing coordinates. You guys will get practice at that in the homework. And we're not going to worry about this in polar. But what I do want to bring up is these regions are much easier to do in polar than they are in rectangular. Now here we have a circle of radius 5. In rectangular, that would be our normal circle, x squared plus y squared equals 25, which is great, but it's not a function. It doesn't pass the vertical line test, so we have some constraints there. That same circle in polar is just r equals 5. So we can kind of start to see when our region is somewhat circular, polar becomes an advantage. It's really noticeable if we wanted to integrate over this piece of a disk, because now we're just integrating between r equals 6 and r equals 4. In rectangular, this would be a mess because we'd have to try and break it into rectangular pieces, and it's really messy. So that's why we're doing the other coordinate systems. Now, if we add the z-axis to polar, that's when we get cylindrical coordinates. So cylindrical is basically polar in the xy plane. So there's the r, and there's the theta between the positive x-axis, and then it just shoots up or down along the z-axis. All the transformations still remain the same. Whoops, sorry. X equals r cosine theta, y equals r sine theta. Z is actually the same in rectangular and cylindrical, and theta is still tangent of y over x. Arctan of y over x, I should say. All right. So cylindrical is not bad. It really is just a 3D extension of polar. And hopefully, you have some familiarity with polar. Now, what we do want to talk about is what happens if we set r, theta, or 0 to a constant. Well, we saw what happens if we set r to a constant in 2D, we get a circle. So in 3D, if r is a constant, we actually get a cylinder that's parallel to the z-axis and centered at the z-axis. If theta is set to a constant, you can kind of start to see the beginning of it here. If we drew in one more line, you really start to see it. What we get is a plane that is perpendicular to the xy plane with an angle of theta between it and the x-axis. And if z is set to a constant, we actually get the same as if we had z set into a constant in rectangular, which is a plane parallel to the xy plane. The reason we talk about these things are called fundamental surfaces. So here's kind of an image. This is from the book, so you can see what's going on. This would be if r is a constant, this would be if theta is a constant, and this is if z is a constant. The reason we want to know fundamental surfaces is if we're looking at a 3D object and part of it is made up by one of these three fundamental surfaces, then we might start to, in particular, these first two. This third one could be rectangular as well. But we see one of these, that's when we start to think, oh, it might be easier to do this in cylindrical coordinates. All right. Now, again, this is going to become more important in Module 4. But for right now, what I want you to take from this is just recognizing the fundamental surfaces, what you get when you set any of these r or theta to a constant, and also the transforming of the points. That'll be something you practice in the homework. So those are cylindrical. Cylindrical is a nice step because you guys have seen polar before, so it's just putting the z-axis onto polar. Questions about cylindrical, and these are just general questions, obviously. I know we're not getting real in depth with this, but I just wanted to bring up the fundamental surfaces so you could see them. All right, let's talk spherical. Spherical looks messy. I mean, you look at all these formulas that just came up. Guys, these are all just right angle trig. All right. They all come from right angle trig. So spherical, what spherical does is now it does the distance from the origin, which is rho, this thing that kind of looks like a P, it's the Greek letter rho. And the only difference between rho and r is stuck in the xy plane. Rho can go anywhere in 3 space. And then we have two angles. We still have theta. Theta is the same as it was for polar. It's between the positive x-axis and the plane that rho lies in. And then this guy here, this guy is called phi, P-H-I. This is an angle made between rho and the positive z-axis. Now I want to show you a couple things. So rho squared is x squared plus y squared plus z squared. This is, if rho were a constant, this would be the formula for a sphere of radius rho, hence the name spherical coordinates. Now, we already know if theta is a constant, we get that plane perpendicular to the xy plane. But if phi is a constant, that means this angle here, then this guy gets rotated around, it actually makes a cone. It's a pretty cool shape. These are our formulas for transforming. As always, guys, you do not need to memorize these. These will be something you can put on your formula sheet. So what I want you to do when you go to work on the homework of going back and forth between the coordinate systems, have these available to you. In fact, we won't get to it today, but the worksheet for 12.4, I was going to give you, you get the transformations anyways. So this worksheet also is some good practice if you need a little extra past the homework. As always, guys, the solutions are in the course content folder under course materials. Now, spherical coordinates have those three fundamental surfaces we just talked about. We won't go through that slide, but here, if phi is a constant, we get a sphere because all the points on a sphere are the same distance from the origin. If theta is a constant, we get that same plane that we got when theta was a constant with polar. And finally, if rho is a constant, we get a cone. So if we have a region that is made up of these fundamental surfaces, like maybe a quarter of a cone, or one that we'll look at in Module 4 is like an ice cream cone, which is a cone on bottom with a sphere on top. That's a hint to us that spherical might be a better system for us to use because it simplifies our formulas. All right. So what I want you to take from 12.4 for right now, I don't want to overburden you with stuff we're not going to be doing until later. But what you want to realize, what you want to focus on when you're going through the homework is how to go back and how to use these conversions to go back and forth between the two systems, and what the fundamental surfaces look like. Those are the two biggest things in 12.4. Because we won't do as much spherical and cylindrical in Module 3. We're going to see it more in Module 4. Just with the order that the materials came up in, we're doing this now to just start to get this idea down, because we're going to be revisiting this when we get into our iterated integrals. Questions at this point? Well, the midterm, the final is not cumulative. It is only going to be on stuff that we do after the midterm. So the question came up, will you be able to fit all the formulas? I think that's ultimately up to you. It depends on what all you put on your note card, how many formulas you need, how big you decide to write them, so on and so forth. So I can't really say that you can, and I can't really say that you can't, because it's going to be different for everybody. Some people may choose to put on the point normal form of a plane. Some people may not, because they're used to it by the time the midterm comes around. What I would say, remember, you got 3x5 note cards, both sides. It is a lot of space. I know it seems like we got a lot of formulas, but as far as fitting them on a note card, it should be reasonable. But some people might want to include examples and stuff, and that does start to take up more space. And guys, one of the things you can do as you're going through the homework, you can start to make your note cards. You can start making your note cards, use them as you go through the homework. And that way you can decide, like, oh, you know what, I didn't need this formula, I'm going to erase it. Or you can decide, hey, I need more space, so I'm going to redo my note cards a little bit smaller. Or I'm going to rewrite the formulas a little bit smaller. So by all means, you're going to have the note cards. You're getting the formulas now. So you can start to think about how you want to do the note cards. Like I said, no restrictions on what you put on there, just to keep it consistent. I've always done the 2 3x5 note cards. Other questions? Okay, guys, that's what I wanted to go through with you today. For the first time all semester, we're going to end a couple minutes early. Normally we're running a few minutes over. I know we didn't get to the 12.4 worksheet, but you're going to get plenty of practice of that in the homework, so I'm not too worried about that one. I really wanted to get through 12.3, so you had a chance to, so you had a chance to use those formulas. So all you got to submit are number 1 and number 2 from 12.3. That's all. The other thing, module 2 take-home problem is now available. So you guys can get that either from the calendar or from the folder with the take-home problems. So feel free, if you have some time, if you want to start looking at those. Those are, again, not due until the midterm, but if you guys want to turn them in early, I am totally fine with that. Just make sure you follow submission guidelines in more, okay? All right, guys, if you don't have any questions, that's it for today. But if you have questions, we got a couple minutes left, so let me know. As always, I'll be putting up the, no problem. I'll be putting up the recording. Hopefully I'll get it up there tonight. I sometimes forget tonight, but it'll be up there.